The construction of the Brunsttobelbridge in Austria was a comprehensive and technically ambitious project, which saw the replacement of an aging bridge over the Weisach River. The previous bridge, which connected Doren and Krumbach along the L4 Dorener Street, was originally built in 1939, suffered substantial damage during World War II, and was partially reconstructed in 1945 before being reopened to traffic in 1949. Despite improvements made in 1979 to increase its load-bearing capacity, a 2013 inspection revealed significant deterioration that necessitated a complete replacement. The new Brunsttobelbridge was designed by Scheimetter Consult as a three-span pre-stressed concrete structure. The design featured spans of 38 meters, 51 meters, and 38 meters, totaling 127 meters in length. The cross-section of the bridge consisted of slabs with variable heights, 2 meters at the middle of the span and 3.5 meters at the base, giving the structure a total width of 10.5 meters. This design ensured a more stable and durable bridge that could handle increased traffic and provide greater safety. The bridge's construction strategy was carefully planned to minimize traffic disruptions. The new structure was built adjacent to the existing bridge, allowing traffic to continue flowing on the old bridge during most of the construction phase. This method also allowed for a smoother transition between the old and new bridge once the latter was completed. Foundation and early construction. 2013 February 2014 construction began on the 23rd of September 2013 with initial preparations such as site establishment and clearing work. By the 9th of October, the foundation work for the Krumbach Pier had commenced. The project faced challenging conditions, including difficult soil properties and restricted construction space. However, through professional planning and work preparations, these issues were managed efficiently. During the winter months, construction continued to progress on the piers to maintain the ambitious timeline, and by the end of February 2014, the foundation work was completed. The foundation for the piers was achieved through the use of deep wells up to 9 meters, constructed using the shotcrete method. Additionally, permanent anchors up to 29 meters long were installed to manage the horizontal loads at the abutments. Despite unfavorable subsoil properties, the project overcame these difficulties through deep foundations achieved with drilled micro-piles. Piers, false work, and supporting structure. March to December 2014, with foundation work completed, attention shifted to the piers and abutments, which were finalized by May 2014. The next major milestone was the erection of false work. Due to topographical constraints, conventional lifting of the massive lattice girders was not feasible. Instead, a sliding method was employed to assemble the false work, a technique that required meticulous planning and precision. The false work, with a total weight of 900 tons, was designed to support the partially completed structure along with the formwork, which altogether weighed around 3,000 tons. Maximum deflections of up to 19 centimeters were accounted for in the central section, demonstrating the complexity of the task. With the road equipment and bridge railings installed, Vorderwalder Straße was reopened to traffic. The project had reached a significant milestone, but it was not yet fully complete. Demolition of the old bridge and renaturation, October 2015. In late August 2015, the final phase of the project began with the demolition of the old Brunsttobelbridge. This task required careful planning to avoid compromising the stability of the steel structures. The initial demolition focused on removing the asphalt and concrete slabs, followed by separating and lifting out the cross-girder assemblies and main girders. Pendulum supports were secured with steel cables and subsequently dismantled and removed. After the old bridge was fully disassembled, renaturation work commenced in October 2015. This phase aimed to restore the environment around the Weisach riverbed, bringing the project to a close. Achievements and challenges. The Brunsttobelbridge project was marked by several notable achievements. Despite the challenges posed by difficult ground conditions, a restricted construction site, and an ambitious schedule, the project was completed on time and within the expected quality standards. The key to success was the high level of coordination, teamwork, and dedication demonstrated by all involved. Specialized teams and expert planning allowed the construction work to advance smoothly, overcoming obstacles that could have derailed the project. The success of the Brunsttobelbridge project is a testament to effective collaboration and professionalism in tackling demanding civil engineering projects. The new bridge not only improved traffic safety and road alignment, but also demonstrated advancements in construction methods and planning efficiency. Osmangazi Bridge construction. A time-lapse of achievements, the Osmangazi Bridge stands as an engineering marvel and a significant feat of international cooperation and technological transfer. The suspension bridge, part of the Gebze-Orhangazi-Izmir motorway project, connects the northern town of Gebze with Orhangazi in the south. Its strategic importance in Turkey's transport infrastructure is immense, as it drastically reduces travel time between Istanbul and Izmir by bypassing the lengthy coastline route. The construction of this 1,550-meter main span bridge was not only ambitious due to its length, making it the fourth longest suspension bridge in the world, but also due to the challenges overcome in completing the project in a record-breaking 42 months. Construction overview. Key phases. The construction of the Osmangazi Bridge was broadly divided into 5 significant phases. Anchorage work on north and south coasts, main tower foundation work manufacture and installation of main towers, cable installation manufacture, and installation of stiffening girders. Each phase required advanced engineering techniques and meticulous planning, executed seamlessly by Turkish, Japanese, and international engineers. The bridge was built with the combined expertise from the IHI Group, which drew upon their past experience in iconic projects such as Japan's Shikoku Bridge. Anchorage construction. The backbone of stability, the anchorages are fundamental elements in any suspension bridge, as they securely hold the main cables in place. On the northern coast, where the ground is solid, the construction team excavated directly into the bedrock and poured massive concrete structures. Conversely, the softer southern coast required more comprehensive groundwork. Here, the engineers employed a diaphragm wall, a robust containment structure, to reinforce the area before backfilling and completing the concrete anchorages. The differing geological conditions on either side demanded an adaptive approach, illustrating how the construction teams merged technical knowledge with the realities of local terrain. Main tower foundations. Innovation meets stability. The main tower foundation construction required not only stability but also seismic resilience. To achieve these goals, the construction utilized a combination of concrete caissons and steel concrete composite shafts. Concrete caissons, pre-constructed on land, were subsequently transported and filled with seawater to sink to their designated depths. Upon reaching the intended level, the caissons were installed on a prepared bed of crushed rock on the seafloor. This approach employed the world's first seismic isolation mechanism for a suspension bridge, demonstrating a critical innovation that balances stability and safety in seismic zones. This robust foundation design laid the groundwork for the successful construction of the main towers. Steel main towers, precision and speed suspension bridges traditionally use concrete towers. However, in order to accelerate construction, the Osmangazi Bridge adopted steel towers. By doing so, the construction timeline could overlap the manufacturing of steel blocks for the towers with the foundation work. The steel blocks were fabricated in Turkey's own steel factories, creating an efficient logistical flow. The assembly of these steel blocks took a dual approach. The lower halves of the towers were lifted and placed using a 1,200-ton floating crane. For the upper sections, a jib climbing crane was used, which was installed on a horizontal beam lower in the structure. This dual crane approach enabled the completion of both the north and south main towers within just 6 months, a remarkable feat in large-scale infrastructure projects. The bridge construction was managed by a joint venture called Nomayg JV, comprising 5 Turkish companies, Nural, Ozalton, Mangyeong, Yüksel, and Göke, and an Italian construction company, Astaldi. The tender for the project was initiated in April 2009, following an international build-operate-transfer (BOT) model. The total estimated cost for the entire highway, which stretched from Gebze to Bursa, was around 11 billion. The groundbreaking ceremony for the bridge took place on the 30th of March 2013 under the leadership of then Prime Minister Recep Tayyip Erdogan. After a relatively quick construction phase, the bridge was completed on the 30th of June 2016 and opened to traffic the next day on the 1st July 2016. At the time of its opening, the bridge became the longest suspension bridge in Turkey and the 4th longest in the world by the length of its central span. However, by 2023, it had moved to the 7th position in global rankings due to new additions like the Kanakale 1915 bridge. The Japanese firm IHI Infrastructure System Company, which had a strong track record of infrastructure projects in Turkey, including the second Bosphorus Bridge, was awarded the bridge contract on an engineering, procurement, and construction (EPC) basis on the 16th of July 2011. IHI subcontracted the design works to the Danish engineering firm COWIAS, which in turn collaborated with Dissing plus Whiteling for aesthetic design elements. The contract was structured under the FIDIC Silverbook terms, a standard widely used for turnkey infrastructure projects. Construction officially commenced on the 1st of January 2013, and the project was planned to be completed in 37 months. Some key dimensions of the bridge are as follows. Main span length, 1,550 meters, 5,090 feet. Side spans length, 566 meters, 1,857 feet. Clearance, 64 meters, 210 feet. Tower height, 252 meters, 827 feet. Deck size, 35.93 meters times 4.75 meters, 118 feet times 16 feet. Approximately 34,000 tons of steel were sourced from Liberty Galati in Romania for the construction of the bridge, ensuring durability and stability. The next major challenge involved the installation of the main cables, which were critical to the bridge's structural integrity. Aerial scaffolding, known as catwalks, were set up to facilitate this delicate phase. The project used a technique known as the prefabricated parallel wire strand (PPWS) method. In this method, pre-bundled strands of wire, assembled in factories, were extended between the north and south towers on-site to gradually form the massive main cables. This approach not only improved construction speed, but also ensured the consistency and quality of the cables, a vital aspect for the long-term durability of the bridge. With the main towers and cables in place, the final structural component was the stiffening girders, which create the road deck on which vehicles travel. The stiffening girders feature a flat, hexagonal cross-section, a design chosen for its superior resistance to wind-induced vibrations. The construction team used different methods to lift these girders into position. Near the main towers, the blocks were lifted with the 1,200-ton floating crane. For the majority of the deck, however, a lifting device was installed directly on the main cables, allowing sections to be lifted directly from barges beneath the bridge. This dual lifting strategy allowed for simultaneous work at 4 locations, accelerating the process to install roughly 2 kilometers of stiffening girders in just 3 weeks. The speed of the deck installation was unprecedented, and the concurrent execution of other necessary works, such as paving and lighting installations, enabled the bridge to be opened to traffic just 2 months later. Symbol of achievement, a joint effort between nations, the Osmangazi Bridge was not just a testament to modern engineering, but also a symbol of collaboration between Japan and Turkey. The construction drew upon Japan's extensive experience in suspension bridges, transferring essential knowledge and expertise to Turkish engineers. The partnership between the two nations, which included both veteran engineers from Japan's Honshu Shikoku Bridge project and young Turkish engineers eager to master these new technologies, created a bridge that was not only structurally sound, but also an example of effective international cooperation. The excitement around the project culminated in an opening ceremony, attended by senior Turkish government officials, including the president. This celebration was not only a commemoration of the bridge's construction, but also a moment to recognize the labor force that had made the difficult and ambitious project a reality. As with any large-scale construction project, challenges were inevitable. One such setback occurred on the 21st of March 2015 when a catwalk broke away from its bolted joint cable on the South Tower during construction. This catwalk was crucial for workers to access the other side of the bay and had been installed a month earlier. Fortunately, due to the windy weather conditions at the time, no workers were present on the catwalk, preventing any injuries. However, the incident was serious enough to warrant a temporary halt in marine traffic to and from Izmit Bay. Recovery efforts were initiated promptly, and by the 23rd of March, the cable was safely retrieved and marine traffic resumed. The incident was not only a technical challenge, but also had a profound impact on the people involved in the project. The Osmangazi Bridge, officially known as the Osmangazi Bridge, Turkish Osmangazi Köprüsü, stands as one of Turkey's most significant infrastructural feats. The suspension bridge spans the Gulf of Izmit at its narrowest point, linking the city of Gebze with the province of Yalova. It is a crucial part of the O5 motorway, playing an essential role in reducing travel time and distance between Istanbul and Izmir. This immense project was a combination of engineering prowess and international collaboration, resulting in a modern marvel that continues to facilitate economic and social integration within Turkey. The Osmangazi Bridge is more than a physical structure connecting two shores. It symbolizes technological achievement, international cooperation, and efficient project execution. From the careful construction of anchorages, the innovative main tower foundations, and the rapid assembly of steel towers, to the cable installation and the swift completion of the stiffening girders, every phase of the bridge's construction reflected a sophisticated blend of precision engineering and adaptive problem-solving. Completed in just 42 months, the Osmangazi Bridge is not only the longest bridge in Turkey, but also a vital link in the country's transportation network, offering new economic and social opportunities. More than a physical link, it represents a triumph of engineering and collaboration. A bridge not just across water, but between nations and generations of engineers. The Honam high-speed railway is a major transportation project in South Korea, designed to improve connectivity and reduce travel time between key regions. As part of this ambitious infrastructure project, the construction of the Mangyeong River Bridge in Section 3-3 is being executed using a highly efficient and reliable method known as the PSM, precast span method. This method is critical to achieving both structural integrity and project efficiency for this high-speed railway section. The Mangyeong River Bridge is a significant structure in Section 3-3 of the Honam high-speed railway. High-speed railways demand exceptional precision in both design and construction to support safe and stable operations at high velocities. Consequently, the construction of bridges like the Mangyeong River Bridge is a complex endeavor requiring specialized techniques. The PSM, precast span method, was chosen due to its numerous advantages in terms of quality control, safety, and efficiency. What is the PSM, precast span method? The PSM, precast span method, is a construction technique that involves the prefabrication of bridge components, in this case, box girders, in a controlled factory environment. A box girder is a structural element that supports the weight of the bridge and is essential for stability. The standard span length for each box girder used in this project is 25 meters. Once these girders are manufactured in a factory setting, they are transported to the construction site using specialized vehicles and heavy machinery. The core principle of PSM is to maximize the precision and quality of the bridge components by moving much of the construction process off-site. Factory environments offer ideal conditions for controlling material quality, ensuring precise measurements, and optimizing production processes. This level of control is difficult to achieve in traditional on-site construction, which is subject to weather conditions and other external factors. Once transported, the prefabricated girders are lifted into place using large cranes and other specialized equipment. This installation process is faster and more efficient compared to conventional methods. Benefits of the PSM construction method: the use of the precast span method in constructing the Mangyeong River Bridge brings several notable advantages. Enhanced quality control. The PSM allows for strict control over the production environment, which leads to a higher level of precision and consistency in the bridge components. By producing box girders in a factory, the project ensures that each girder meets stringent quality standards before being transported to the site. This reduces the risk of errors that can arise in on-site fabrication. Increased construction efficiency. Traditional bridge construction methods often involve significant amounts of on-site work, which can be time-consuming and labor-intensive. By shifting much of the work to a factory, the PSM method speeds up the overall construction process. Once the prefabricated girders arrive at the site, they can be installed quickly using specialized equipment, minimizing disruptions to nearby areas and reducing construction times. Improved safety and reduced environmental impact. The PSM method reduces the number of workers and machinery required at the construction site, leading to fewer on-site accidents and a safer working environment. Additionally, by manufacturing girders in a factory, there is less need for large-scale equipment operations on-site, which can lessen the environmental footprint of the project. Cost effectiveness. The streamlined construction process not only saves time, but also reduces labor costs and materials wastage. This results in significant cost savings for large-scale projects like the Mangyeong River Bridge. The steel plates are first preheated to make them more malleable. They are then bent into cylindrical shapes using heavy-duty rollers. This process, which takes between 4 to 6 hours, is computer-controlled to maintain precision. The finished pipes must meet exact specifications to ensure proper alignment and structural integrity. The edges of the plates are precisely prepared for welding. Before the plates are joined, the metal is heated to the required temperature, which prevents cracking during the welding process. A welding robot creates the final weld seam, a task that takes up to 16 hours per pipe. Throughout this time, the weld must remain at a consistent temperature to avoid any weaknesses in the joint. The integrity of each weld is verified through multiple inspections, which include visual checks and advanced magnetic testing. Once welded, the seam is ground smooth, and 4 injection holes are drilled into each pipe. These holes serve a critical purpose during installation, allowing concrete to be injected between the pipe and the surrounding rock to provide additional support and stability. The next phase involves transporting these massive pipes, each weighing up to 20 tons, to the construction site. The pipes are moved up the mountainside via a specialized construction cableway, with each journey meticulously planned to avoid delays and disruptions. Transporting over 800 pipes to the installation site presents a significant logistical challenge, particularly because the only access to the site is through narrow tunnels. Upon reaching the top of the mountain, the pipes are taken through a 3-kilometer tunnel and further transported to various sections of the construction site. This process demands precise coordination, as any traffic within the tunnel must be strictly one way due to its narrowness. Once the pipes arrive at their designated area, 3 pipes are welded together to form longer sections. This pre-assembly reduces the number of welds needed during the final installation in the pressure shafts, which are inclined at a 40-degree angle. Working in these steep shafts is physically demanding and requires skilled labor. Each weld in the shaft is carried out manually by expert welders, known for their precision and craftsmanship. Quality assurance is a crucial aspect of steel hydraulic engineering. Each weld undergoes several rounds of inspections to guarantee it can withstand the high pressures in the tunnels. One critical method involves magnetically testing the seams using a fluorescent liquid. This technique reveals any potential defects, which can then be rectified before the pipe is lowered into its final position. Once the pipes are fully installed, they receive a final anti-corrosion coating to protect against rust and prolong their operational life. These comprehensive measures ensure the pipes are capable of enduring the high water pressure and environmental conditions within the tunnels. Steel hydraulic engineering involves the construction and installation of steel components in hydraulic structures, dams, tunnels, and pumped storage power plants. It plays a critical role in projects that manage the movement and containment of water under high pressure. One notable example of steel hydraulic engineering can be seen in the Limmern pumped storage plant in Switzerland, a massive infrastructure project designed to enhance the country's energy storage and electricity production capacity. The Limmern pumped storage plant is situated between 2 alpine lakes, Lake Limmern and Lake Mutsi. As one of the most significant expansion projects undertaken by the energy company Axpo, this power plant aims to store and generate electricity through a sophisticated process of water transfer. During periods of low electricity demand, water is pumped from Lake Limmern up to Lake Mutsi, which lies approximately 630 meters higher. When energy demand peaks, the stored water is released back down to Lake Limmern through steep pressure shafts, powering turbines to generate electricity.